Welcome to qnawire.
So essentially, when an elephant dives underwater, its trunk can act as a snorkel in a sense. So when it's breathing, its lungs are actually at atmospheric pressure. However, all of its internal organs and everything around the lungs are at an increased pressure because, of course, they are underwater. And the difference in pressure between the lungs and the everything else around it, the internal organs of the elephant, must be compensated by the diaphragm of the elephant. So the diaphragm of an elephant must be extremely strong in order to account for this pressure difference, and allow the elephant to breathe underwater with its trunk acting as a snorkel. So essentially, one can say that we have the area of the diaphragm can be approximated as the uh, area of a circle, and this is of course going to be pi r squared. We have a diameter, so we're going to have to substitute for that. And here the diameter is going to be 120 centimeters. So 120 centimeters we know is going to be 1.2 meters. So we can just convert that really easily. 1.2 meters divided by 2 squared. And that's going to give us 1.13 meters squared. So this would be the surface area of the diaphragm. Now, we can define a force as a pressure times an area, which means that the maximum pressure can be defined as the maximum force that the diaphragm can withstand divided by that cross-sectional area of the diaphragm. This is going to be equal to the maximum force that the diaphragm can withstand, being 24,000 newtons. Dividing this by the cross-sectional area of the diaphragm being 1.13 meters squared, and we find that the maximum pressure that the diaphragm of an elephant can withstand is 21,220.65 newtons per meter squared. Newtons per meter squared is also known as, of course, pascals. So, and at this point, we can convert this into millimeters of mercury. So we can convert this into millimeters of mercury by, first of all, the density of mercury being 13,600 kilograms per meter cubed. And then we can define a pressure being a density of mercury times the acceleration due to gravity times a height of mercury. And we are simply going to isolate this variable and solve. So this would become the height equals the pressure max divided by the density of mercury times the acceleration due to gravity. Solving for this, we see that we're going to have 21,220.65 pascals divided by the density of mercury being 13,600 times the acceleration due to gravity. And this is going to be 0.159 meters. Converting this is going to be approximately 160 millimeters of mercury. So essentially, this is going to be the maximum pressure, but in terms of millimeters of mercury, we have to use this little conversion here. And after plugging in for our constants and the density of mercury, we find that this is the maximum pressure that the diaphragm can withstand. And the correct answer choice for this is going to be answer choice A. So answer choice A would be the correct maximum pressure that this elephant's diaphragm can withstand. And that's the end of the solution. Thank you for watching.